key crypto systems. The public key crypto systems can be used for three functionalities, mainly encryption, decryption, key exchange, and digital signature. And you for your syllabus, you will be having RSA algorithm, that is Rivest, Shamir, and Edelman. Then ECC, elliptic cryptography algorithm. Then Diffie-Hellman key exchange algorithm and DSA algorithm. Now, first we'll see the RSA algorithm, that is Rivest, Shamir, and Edelman. So this RSA algorithm is a asymmetric key or public key cryptography developed by three cryptographers, namely Rod Rivest, Adi Shamir, and Len Edelman. So they were the persons who were involved in the development of this algorithm, which is a block cipher asymmetric key algorithm. Okay, this algorithm can be mainly used for all the three aspects of PKCS, that is public key crypto system, that is encryption, decryption, then exchange of the keys, and for the digital signature, okay, which is for authentication. Now we'll see how this algorithm can be used and what is the process involved. So for all the public key crypto systems, we make use of the prime number as one of the element for these algorithms. So all of you should know what is a prime number. What is a prime number? A prime number is a number that does not have factors apart from it's the same number and 1. So you do not have anything to divide. You cannot have any divisor or any factors apart from 1 and the number itself. Okay, for example, 3, 5, 7. These are all prime numbers. If you take it is an odd number, but it's not a prime number. Okay, so this kind of this prime number is generally used for our public key crypto systems in general. Okay, now RSA is also using the will make use of the prime numbers, and we are initially what we are doing is the process of generation of keys is important in the RSA algorithm. So how do we generate the keys? Number one is the first step is select two large prime numbers. Let us name it as P and Q, such that P is not equal to Q. Can you understand? First step of generating the process of key is select two large prime numbers, namely P and Q, such that P is not equal to Q. That is the first point. Second point is calculate N. N is a one variable. N is equal to P into Q. Okay. This N is also a large number. Typically, a minimum of 512 bits. Minimum, it should have 512 bits. Can you understand? So that is the second step. Now we have generated the two points in which we generate the RSA modulus, which will be used for further steps, that is for encryption and decryption. So the third important step is take a number E which must be greater than 1 and less than P minus 1, Q minus 1. For example, if P is 23 and Q is 41, so a number E we must select so that it must be greater than 1 and less than P minus 1, Q minus 1. There must be no common factor for E and P minus 1, Q minus 1. Okay, except 1. Okay, so in other words, two numbers E and P minus 1, Q minus must be co-prime. Okay, they must be co-prime. Okay, now we have got E also. Now already we have PQ and N. With that we make use of N and we have derived E. Okay, next one is the formation of the public key. The pairs of keys for public key in RSA is E, N. What is E? Just now we have generated. That is E must be any number must be, there must not be a common factor for E and P minus 1. So E and P minus 1, Q minus 1 must be a coprime. So that is E, and N already we have. Okay. So this forms the public key pair. That is E comma N forms the public key pair. That is the fourth important point. Okay. Now, next one, now we have the public key. What we need the private key. Since it is a public key cryptography or crypto system, we need to have all the pair components. Okay, in order to change the plain text into ciphertext. Now let us take the fifth point of this algorithm, that is generation of the private key. Let the private key be named as D, and which is calculated from P comma E comma E. Sorry, P comma Q comma E. We have to calculate the value of D, that is the private key, from the values P, Q, and E. Okay. Now, for a given N and E, there will be a unique D. Okay. So here we are using the mathematical concepts where can you see this? ED or DE is equal to 1 mod P minus 1 Q minus 1. So we are using the modular arithmetic, Euler's theorem, Euler's torsion theorem, etc. That mathematical concepts we are using it here, where we must know what is the value of D from a relationship which is written as DE is equal to 1 mod P minus 1 Q minus 1. Okay. Now this is what we have. So therefore D can be E inverse mod P minus 1 Q minus 1. You know that mathematically we can write that D is equal to E inverse. The E will go this side, means to the right hand side, means D is equal to E inverse mod P minus 1 Q minus 1. Okay. So now we have got E, that is the public key, and D is the private key. Now what is the pair? N comma E, E comma N is the public key pairs. Then D comma E is the private key pair. Okay, D comma N. E comma N is the public key pair, and D comma N is the private key pair. So we have all these parameters. So now we want to generate the ciphertext using RSA algorithm. Okay, so the ciphertext of generating or doing the encryption using RSA algorithm for a plain text P is calculated as, you can see this, calculated as C, that is ciphertext is equal to P power E mod N. Can you understand what is C? C is the ciphertext. And what is P? P is the plain text. What is E? E comma N is what? E comma N is our public key pair. E is the public key. Okay, so you making use of the public key, we are able to generate the ciphertext as C is equal to P power E mod N, where what is P? P is a plain text, and what is E? E is a public key. And N already you know it is P minus N is equal to P into Q. What is P into Q? They are two large prime numbers. So this mathematical step explains the way of creating or generating the ciphertext from the public key. Now what we need, this message goes to the recipient. The recipient has to perform the decryption process. So decryption process he has to perform. How he will perform is, he needs the plain text, that is he needs P. So he will calculate, or he will generate the P as P is equal to C power D mod N. Can you understand? P is equal to C power D mod N. What is D? D is the private key. Who will possess the private key? Only the person who can, the D is known only to the either the sender or the recipient. Okay, but E is known to both sender and recipient. Can you understand? E comma N is known to both sender and n is known to both. E comma n is known to both sender and the recipient in RSA, but D, which is a private key, is known to only the either the recipient or the sender. You can use it in two ways. As I told you in the earlier class, we can use the public key crypto system in two ways. Therefore, the decryption is done as P, that is plain text, is equal to C raised to D mod n. Okay, so therefore we get the plain text from this mathematical formulation. So this is how we perform the decryption using RSA. Can you understand? These are the 6 important steps of RSA algorithm. Once again, I'll repeat. First step is select two large prime numbers P and Q, calculate where P is not equal to Q, and calculate N, which is equal to N is equal to P into Q, and select a number E which must be greater than 1 and less than P minus 1, Q minus 1, where E is nothing but the public key. Okay, E comma N is the formation of the public key which can be used for RSA encryption. That is the third point. Fourth point is select a private key D from the mathematical formulation where D is equal to E inverse mod P minus 1 Q minus 1. Okay, so what is D? D is the private key. Okay, that is the fourth important point. Next one, calculate the ciphertext perform the encryption as using the parameters that is P, E and N as C is equal to P power E mod N. That is the fifth point. And the sixth point is, in order to perform the decryption, we need the parameters, that is, we need ciphertext. We need the private key. We need the value of N. So the plain text is calculated, that is, decryption is done by P is equal to C power D mod N. Can you all understand? So these are the 6 important steps in our RSA algorithm. Let us take an example. You can see on the screen an example. Let there be two prime numbers, P is equal to 7 and Q is equal to 13. So we calculate the modulus as N is equal to P into Q, that is 7 into 13, which is 91. Select E, okay, which is what the condition is, there should not be any common factor between E and the P minus 1 and Q minus 1. What is P minus 1? 6. What is Q minus 1? 12. 6 into 12, 72. And between E, whatever you select, between E, that is value of E, you are selected 5. And 72, there should not be any common factor except 1. So between 5 and 72, there is no common factor. Okay, only 1 is the common factor. So therefore, E can be selected, chosen. E is chosen. Now, what do we have? We have the prime public key, that is E comma N, that is 91 is the E is the 5 comma 91. 5 is the public key and 91 is the value of N, the modulus N. Now we have to calculate the what we have to calculate. We need the value of D. So D is equal to, what is D is equal to? D is equal to E inverse mod P minus 1 Q minus 1. So therefore D is, you can see here, D is, using the Euclidean algorithm, we are calculating the value of D, which is equal to 29 from D is equal to what? E inverse. E is what? 5. 5 inverse mod P minus 1 Q minus 1. That is 5 inverse mod 72. So you get, this is done using the Euclidean algorithm. So from this example, we get the value of D as 29. Okay, now we have the private key, that is 29 and 91. That is a value of N. So D comma N is the private key pair and E comma N is the public key pair. So 5 comma 91 is public key and 29, 91 is the private key. So we have all the components, parameters. So we can straight away go for converting the plain text into ciphertext. So for example, if the plain text is 10, so we can calculate the ciphertext as, you can see I'll highlight as C is equal to, what is C? Ciphertext. What is the value mathematical formulation? C is equal to P power E mod N. Okay, so therefore we have 10. P is what? Plain text. For this example you have taken, P plain text value is 10. So 10 power 5 mod 91. You have to calculate that. That will be the ciphertext. Okay, that is the value of C. C, that is ciphertext. So we got the value of C from this formulation as 81, 82. Okay, now the value of C is 82. Now using the C and D comma N, that is private key, what we have to get? We need to get the plain text. What is our plain text? We have to get P is equal to 10. If you don't get P is equal to 10, the answer is wrong. Okay, so you can just see the plain text, that is plain text is equal to 82 power D. What is 82? 82 is ciphertext. What is 29? 29 is the private key value of D. So 82 power D, C power D mod N. Therefore 82 power 29 mod N, mod 91. 82 power 29 mod 91. The value when you calculate will be equal to 10. So therefore it is correct. Suppose this value is not 10 or 12 or something you are getting, means definitely it is wrong. Something has happened. Can you all understand? So this is what your RSA algorithm. Any questions you have in this?